Okay, suppose we have a group of collected birthdays. So a class activity where you collect a birthday from everyone and you just go out to a group of people and get a lot of birthdays. For a given group of people, what's the probability that any two of them share a birthday? If I've only got one person, then the probability is zero, obviously, because there is no other person. And if I have more than 365 people, then I know the probability is 1, because at some point, if you've got more people than there are days in the year, someone has to share a birthday. But in between, what's the probability? And often we tend to focus on rare events. It should be rare. If I've only got a couple of people and it's 365 days in a year, chances are they're not going to share a birthday. I'd be very surprised if they did. If I had hundreds of people, I would be very surprised if they didn't. So I know somewhere in between is a sweet spot where we know the probabilities must increase. But how would I actually do that calculation? You can't really do the calculation the way we do some probabilities, where you actually calculate the probability of it happening, because it's such an open-ended problem and there's so many people involved. So this is one of those cases where we look at the very simple basic probability formula, that the probability of something happening is equal to 1 minus the probability of it not happening. So that's how we're going to do this calculation. We're actually going to calculate the probability that a group of people do not share a birthday. If we subtract that from 1, we'll have the probability that they do. So here on this page, we have the basic probability associated with one person. Suppose the first person comes in to give us their birthday. They have 365 choices for birthdays that they can work with. There's no chance that they're going to, the 100% chance they will not match because there are no other people. So we're able to say that the probability of matching is 0 for one person. So that's a pretty simple, trivial part of the problem. Let's look at a second person. The second person coming in only has 364 days left to choose from, because the first person took one of those days. So the probability of not matching is going to change. It's going to be the 364 divided by 365. And that's the probability of not matching the birthday. So there's only a 99.7% chance that the second person picking a day is not going to share the birthday of the first person. Okay, so we've already increased to 0.3% chance that they will share a birthday, which is a pretty low probability, so we don't worry about it too much. But let's take a look at the third person coming in. The third person coming in, there's only 363 days left, so they only have a 99.5% chance of not matching one of the first two people as we go through. But now it's time to talk about this central column. So it's really what we care about is not just that each person has a probability of matching someone else. The second person has a 99.7% chance of matching the first person. The third person has a 99.5% chance of matching either of the first two. But we don't just want to know that. We want to know the cumulative probability that nobody matches. So A and B and C. So we actually have to take the product of all these probabilities as we go through. So for each person taking it, we have the overall probability we've already achieved. For the third person, that's the 99.7% probability from the second person, times the 99.5% probability of the third person. That's how we get the 99.2. So we're looking at this equation up here as the one we're actually implementing. So each time we add another person, we're making the equation longer. So it's the 364 over 365. That's the probability of the second person, first person. 365 minus 2, 365 minus 3. So the equation get longer and longer each time. So I jump past the 3 people. Let's jump all the way out to 10 people. At 10 people, each person in the list has had one less day than the person above them in the list, and therefore their probability of not matching someone else starts to come down. By the 10th person only has 356 days to choose from, so they only have a 97.5% chance of not matching one of the first 9. But cumulatively, we're already down to an 88.3% chance that none of the 2 people in the first 10 have matched each other, which means we have an 11.7% chance that they do, in fact, match a birthday. So if within the first 10 we had a birthday match, we'd be surprised but not stunned, because 11.7% of the time we would expect that to happen. So let's jump out to 30 people now as we go through. So if I scroll down here to see the 30th person only has 336 days left to choose from and only has a 92.1% chance of matching someone else. So that 30th person doesn't really expect to match someone else. But by this point, with the cumulative probability, we're down to a 29.4% chance of these 30 people not sharing the same birthday. So we're actually getting to the point where there's a bigger chance that they will than that they won't. There's actually a 70.6% chance that they will share a birthday. So you think about the size of a class or the size of the group that you've picked. If there's 30 or more people, it starts to get pretty likely that the two people in the group will share a birthday. And that's not necessarily intuitively obvious. The reality is that there's 365 days. If you take 30 days, you don't really expect 30 people out of the 365 days to have had a match, but in fact they will. The probability starts to show us that it's very, very likely they will share our birthday. So let's fill out the rest of the year now and work our way down. So, if I look at our class, a class where 104 people reported in one of the sections of this class, the 104th person had 262 days left and was already down. Just that individual alone had a 71.8% chance of matching someone. In terms of the cumulative probability, you can see how small that number is. 0.000000834. That's a pretty low percent probability of someone along the way not having matched. So the reality is, by the time we get to 104, we expect to have had a match as we go through. There's a 99.99999% probability that in the first 104 people, you will have had a match. And in fact, that statistic gets worse and worse and worse as you go on, because by the 200th person in this spreadsheet it lists, we're already reporting 0 and 100. That's not the real number. It's just that the decimals are so small that Excel can't calculate them anymore. And we really do expect to have a lot of hits as we go through. So here's the graph we're talking about. And in terms of the X scale, I only go up to about 60. So by 60 people, there's a 100% chance we expect to have those birthdays match. The magic number tends to be in here in the 30-40 range as we go through. That's where you really start to get up. By the time you get to 40, you're above 90% probability as you go through. In fact, for this video, I recorded two different classes. One was a fairly small class, and one was a fairly large class. In the small class, 16 people reported their birthday. And in fact, they had a 28.4% chance already of matching on a birthday. And with 16 people in the class, there in fact were no matches. So the probability played out, the 71% chance of one, and none of the first 16 people in that class shared a birthday. But working our way down in the other section where we collected data, the 30th person actually did match. We got a match on 30 people. So it was a 70.6% chance there would be a match. We're not that surprised that they were. In fact, the 40th person also matched. So we actually had a second person matching. At that point, there was almost a 90% chance we were going to have at least one match, and we actually already had two. So if I look at the data for this larger class, here's a list of the 11 different days that people matched. That's 12% of the 104 people that matched. So if you think people matching birthdays when chosen at random is rare, at only 104 people, there were already 11 birthdays that matched. That's 22 people out of the 104 actually shared a birthday with someone else. So if you think matched birthdays would be rare, what's really rare would be to get 104 people and not have them match. The odds of that happening, even though it's less than a third of the possible days, the odds of 104 people being chosen at random and not sharing a birthday is infinitesimally small. In another class I did this with, there were 143 people that report, and look at this data. So in this class, we had lots and lots of people who shared a birthday, lots of dates. But in fact, we had a slew of days, 7 days, where 3 people shared the same birthday. And this is in one group of 143 people. So that speaks to the fact that in our spreadsheet, the curve climbs so quickly. So it's one thing to say that the first one might not show up until 20 or 30 people, and the second one might not show up to 40. But by the time you got 100 people, which is way off this scale, we had 11 people. And at 143 people, we had 30 or more going through. So the probability of a match, of a rare event happening, is remarkably high. Like I said, in this class, it was very, very large. And that's what I would expect as I go through. So this class, it was 104. So you look at that, 99.99999, 5 nines to the right of the decimal place. So I come down here to the 143 layer, that other class on the PowerPoint slide. Look at that, 99.99999999991%. It's vanishingly small. You knew you were going to have a hit, and in fact, we had a lot of hits. 30 or more people out of the 143 shared a birthday. 22 shared just in the first 104 of this other class. So the moral here is that to do the calculation, you can't calculate the probability that people will match on their birthdays. It's just too open-ended a problem. You won't get a number between 0 and 1 if you do that calculation. So instead, you have to do the calculation of the odds of it not happening. So the rare event is you pick n people and none of them match a birthday. That's the calculation we're actually doing in columns B, C, and D. Column E is just 1 minus column D, and it shows the probability. So rare events do happen. As an engineer, you have to realize that. It's why we engineer things so strictly, is that even something that looks like it would be incredibly rare turns out to be not only common, but actually mandatory as we look at more and more cases over time. So whether that's a lot of people being chosen at random immediately, or you're doing a design that has to be able to last for years and maintain itself in terms of reliability through rare events, recognize that rare events that look like they should almost never happen, in reality, inevitably will as the numbers grow. So that's something very, very important to keep track of as you deal with probabilities. And like I said, the magic tends to be up here in the 30s and 40s. Like I said, in the big class, we had the first match was at 30, the second match was at 40, and by 100, we had 11 matches. So it grows exponentially over time. Keep that in mind for rare events.